Hi, this is Abdul Jabbar from National Instrument Dresden. The title of this component demo is Vertical 5G NR UE Stack Integration. The scope of this component demo is to demonstrate the vertical stack integration of NI FPGA-based UE, PHY, and MAC layers with the third-party 5G NR protocol layer. To do that, the vertically integrated UE stack is going to be tested against a Genode B emulator. This block diagram shows how the setup for this component demo looks like. The Genode B emulator on the left side consists of a real-time playback of NR downlink signals with pre-generated content. Those signals are received in real time by the UE stack, which has been configured via 3GPP compliant RRC test vector injection. Two scenarios are going to be demonstrated. The first scenario is the random access procedure. We will demonstrate the end-to-end signaling test over vertically integrated UE layers. The second scenario will be the high throughput test, where we are going to show a dummy data transmission from the Genode B emulator and data reception on the UE side, which is in RRC connected state. So on the UE side we have L1 only. This slide shows the hardware setup. On the right side we have the Genode B emulator, which has the NR PHY system, controller, and two USRPs. On the left side, we have the UE, which has the NR USRPs, PHY system with related FPGAs, controller, and the Linux server. The execution steps of RAF procedure will be as it's shown in this figure. We will start by the Genode B emulator, then we will start PHY and MAC, and then we will start the high layers inside the Linux server. At the end, we will inject two RRC test vectors. Let's now switch to the demos. Let's now show the random access procedure test. Instead of execute the steps that we have already mentioned manually, a script file has been created to start them automatically. Let's now start our script file. So the first step is to start the Genode B emulator. So what's going on now, the bit files are downloaded to the FPGAs of both USRPs, and then the waveforms are stored in a DRAM. As soon as the USRPs start to transmit the data, we can stop the host, since we have the waveform already inside the FPGA in a playback mode. Now we will start to deploy the project, since we are running the UE from the source code and not from the firmware. It needs approximately 4 minutes. After the UE application deployment and run, the UE starts to connect to RT machine represented by the NR PHY system. As you can see here, the UE, the RRC state of the UE is in idle mode. So now the UE or the application is connected to the RT machine. We will start the high layers on the Linux server, and then we will and then the system will start to inject the test vectors to the NR RRC. The UE starts now to perform a cell search. It's now in a connected state. As you can see here, the NR RRC state is connected. We can see a throughput here since we have just for layer 1 a downlink data on slot 17 and 16. Let's now confirm the RAG procedure using the log files from the high layers. Here is the Linux server. Okay, so this is the last log file that we have already collected. We can have a copy on our local Windows machine. And now let's switch to this folder. Let's search for RAG. We can see the RAG procedure steps in consequence, and at the end we have RAG indication received with success with a timestamp approximately 18 and 11 minutes, which is similar to that of the Windows machine. The second part of this demo is to show a high throughput test. The data transmission and reception at the UE is going to be demonstrated where the UE is in a connected state. So on the UE side, we are using the L1 only. Here is the G-Node B emulator, consists of a real-time playback of 5G NR downlink signals with pre-generated content for the 4 layers. In this demo, we are using 4x4 MIMO. As you can see here, we have 2 USRBs. Each USRB has 2 RF channels. Let's now switch to the UE. We can see 256 QAM modulation scheme for the 4 layers and approximately 2.1 gigabit per second PHY throughput.